Welcome to the workshop about Mina and Protokit. And yeah, in this workshop we're going to show you how to build zero-knowledge application chains on top of Mina using Protokit. And so basically the approach that we're going to take is we're going to talk a bit about like what are the properties and the characteristics, the features of Mina itself. And then we're going to see, okay, like how can we leverage that to build nice applications on top of that, and yeah, what we can leverage to do that. All right. Awesome. Let's start with what is Mina protocol itself. And we're going to talk about the steps from a trusted blockchain networks towards kind of the internet of verifiable applications. And the technique we're going to use for that is zero-knowledge proofs. I'm sure everyone has heard of that already. We're going to talk about that in more detail later on as well. So basically kind of the big iteration that we're going to do here is we're going from trustless to actually verifiable. And not only verifiable, also succinctly verifiable. Yeah. The first kind of big block that we're going to look at is how, like, what our execution environment in this case, and how we can use it for trustless code execution. So far, all of the blockchains, they offered some execution environment that uses decentralized property. And the way they did that is by using consensus and blockchains to offer that replicated environment. And what that means is that every active network participant, they have to execute the same code again and again to actually verify that it has been done correctly. So, and as part of that, they have to store a copy of the whole chain state in order to be able to do that verification. So, example of that are smart contracts, for example. And now what Mina is doing is actually offers a distributed environment where every participant can verify all of everything that's ever happened on that blockchain just by verifying one constant signed proof. And kind of the step that we can think of here is kind of going from having like a monolithic layer, one blockchain, to doing rollups where only interested participants can verify only the stuff that they're interested in and still be sure that everything is valid. So as an example for replicated execution environments, for example, Ethereum, is Solana, is also Bitcoin or any other blockchain that we know that is out there. One of the most fundamental building blocks of doing that is Kimchi, which is a proof system that's native to Mina, that was developed by Mina. And we can use that to actually create that execution environment that we talked about. And as part of Kimchi, we also offer pickles, which is kind of this technique for recursing over Kimchi proofs, which allows us to actually kind of have, like, it's basically infinitely recurse over a large set of proofs to that compress that into one single proof that everyone can verify in a constant time. And so we have three properties of Kimchi here. And the first is that it's distributable. So as soon as you create the Kimchi proof, you can give that any party, and they can verify it independently and trustlessly. It's also privacy enabled. That means that everything that you execute using Kimchi is private by default. So that means that I run the code, I create the proof of the code, and all of the data that I have inside of that will never be leaked to any third party. So that means that, I don't know, I can do my shit on my machine, and I can only leak the stuff that I want to the third party, and the third party can still verify that I did that using my private, unleaked data without actually knowing the data. And the third property is that it's succinct. Succinct means that it doesn't matter how much computation I want to prove. In the end, I will always get a constant size proof that will never change its size, and also that it's going to be verified in a constant amount of time. It's going to take a constant amount of effort to actually do that verification. This means that I can put infinitely many execution steps into one proof and only verify that, which obviously has super nice scalability effects. Awesome. So if we now have this nice proof system where we can execute anything, we can also verify trustlessly. Why do we need consensus still? Because it gives us these three properties. And I'm actually going to start on the right here, which is state synchronization. We want to execute our code on a shared global state where everyone kind of can agree on some source of truth. and some amount of data that is accepted to be true amongst all participants. A second property that we get is censorship resistance, so that we can, through the consensus, be sure that basically everyone who wants to participate can also participate without kind of relying on a single party that can censor or allow anyone in or allow someone not in. Yeah, also a nice property. And then also finality, which is coming hand in hand with the state synchronization property, which means after some time, after some network conditions have been met, basically, we can ensure that some computation, some shared global state is irreversible and will never be rolled back. So now we can take these consensus properties that are true for every blockchain out there, by the way, and we can say, okay, like what additional properties do we get when we take that to our verification-based zk world, right? So the first is execution verification. And the big change here is that it's actually succinctly verifiable. So we can say, okay, like we have this property, we have this blockchain, it has the shared global state and all this execution that has happened on there. And in order for me to verify that that has actually happened and that it's final, we don't have to verify everything that's ever happened. We can only verify that single constant proof in a constant time. And then we have to prove singularity, which means that everything that's ever happened isn't only verifiable succinctly, but it's also kind of compressed into this one proof that I can give anyone without them having knowledge of the current network state, and they can verify that by themselves and also trustlessly. And all of that leads into this model being able to do decentralization at scale, because we can fit as much computation as we want while still having these nice decentralization properties of being able to run full nodes with minimal hardware requirements at the end, which enables a much bigger audience to actually run full nodes and participate actively. Awesome. So basically, just that as a summary, Mina protocols, it has verifiable execution environment and it has a verifiable consensus. That is because Mina not only compresses all of the execution that happens on it into that consistent proof, it also proves the consensus itself. That means that we don't have to run the verification on the consensus. We can also use the same proof and verify the same thing. Awesome. So that was kind of a TLDR of Mina. And now we're going to look at our kind of model for building applications, and we separate it into application and in base layers, and kind of the separation of the responsibilities of those two layers on top of Mina. The first is the application layer, and that is kind of the layer where our applications live, where they will execute their code, where they will store their state, and everything of that execution state it will be proven. And then on the other side we have the base layer, which actually verifies that execution and does some other duties of accumulating those proofs and letting them interop with each other. So basically that we can have application layers that communicate with each other and yeah, are super interactive. So the application layer, what properties do we have on those? Basically, the way we build application layers are something that we call off-chain compute, which means that the code doesn't actually run on the blockchain itself, but we run it outside of that. We run it for like some time frame, and after that, we create a proof of all of those execution, and we take the proof, we go to the base layer and we say, hey, we did all that. Can you verify that we actually did it correctly? And so one of the nice things about having this off-chain execution model is that we are not bound by any like gas limits or block sizes or anything like that. We can super freely and flexibly design our applications layer to our needs, as long as it's provable, obviously. And using that, we can then still, doesn't matter what we actually did, we can go to the base layer and say, okay, please verify this for me. Our application layer obviously is also privacy enabled. Since everything in Kimchi is privacy enabled, we also took that and put it, or kind of get the property for the application layer as well. And as an additional property, we also get that we can be optionally private. We can have some public stuff, some public execution, and we can have private execution. And we can kind of freely choose what we want to do in which part of our execution, which parts we want to keep private, and which part we want to leave public. And then, as I already touched upon, it's customizable. We can freely decide how we want to design that, what we want to actually do. And yeah. Then coming to the base layer, which is kind of the place where all of the applications layer come together, where where verification happens and where a few of other things happen. And coming to the first one, verifiable scaling. That basically means that scaling becomes an issue of the past because we took that model of decoupling the application layer and saying, okay, like do all of your stuff off chain and then only do the verification on chain. And this means that obviously the scalability properties of that base layer become so much better because we don't have to actually run any code on that. We only have to verify it, which makes it so much cheaper to do and therefore gives us better scalability properties. The other thing that we do in the base layer is proof accumulation. Since we already touched upon, Mina is a constant size proof. That means that all of the proofs that we actually give Mina to verify, they also get merged and recursed into that constant size proof. So everything that is in the Mina proof is every application layer that ever was executed on that. And then also we can use the base layer for programmable interoperability, which means that multiple application layers can talk to each other through that base layer. Yeah. Awesome. And the primitives we're going to use for that are shared sequencing. We have a feature called actions on Mina, which allows us to do something like shared sequencing where you have kind of this permissionless framework where sequencing happens on the base layer and then only the execution happens on the application layer, which gives us super nice censorship resistance qualities. The base layer will also serve as the shared liquidity for all this application layer where all the tokens live, all the value is basically stored. And then only if you use an application, you can go to the application layer and bridge tokens in, use them there, but still have the security of the layer 1. And then verifiable settlement. Applications basically run off chain, and then they need to have some point in time where they say, okay, like all my execution that I did off chain, please verify that. That's called settlement, and where all the transfers happen and stuff like that, that's called settlement, and we use the base layer for that, and therefore kind of inherit the security properties of the base layer. Awesome. Here we have some basically infographic where we show how that kind of can look. And on the bottom we have the application layer, and on the top we have the base layer. And we can see that the base layer offers us some things, for example, sequencing, settlement, bridging tokens. And then we have the application layer that can have a variety of implementations. That can be zk rollups, normal circuits, MPC computation, peer-to-peer zk circuits, whatever you can imagine. And they can use settlement, sequencing, interoperability, and liquidity sharing to interoperate with the base layer and have this kind of common subset of truth, while still being having their own identity and their own implementations. Awesome. That was kind of just a primer on what Mina actually kind of offers and what the value proposition is. And now we're going to look at how to actually build using that model. And we're going to touch now quickly on ONJS itself, which is kind of the low-level language that is used to build kimchi circuits. Then we're going to go into Protokit and see how we can build application chains on top of Mina. All right, just kind of a summary of what are the things that we need to actually build verifiable code. And the first primitive that we have are circuits, and circuits is kind of the description of the program that is then later proven. You can kind of imagine this as kind of being a function that outputs proof. So you have a function, you put your code in there, and it outputs a proof of that execution. And then we have ONJS, which is our, as I already touched upon, low-level language to actually build those circuits. And it's actually something that Protokit also uses under the hood. And it's kind of this TypeScript SDK that you can use to really like super nicely and has a really cool API that you can use to actually build those circuits. And then, as part of the output proofs, that those proofs contain public inputs and outputs. And these are kind of the parts of data that are leaked to the outside. And then they have private inputs that stay private on the party that proves them. All right, so let's look at this code. Basically, this code is kind of a low-level, or it's basically kind of what describes a circus. In our case, we want to prove a program that increments a counter by only one at a time. So what we define here at the beginning is the counter state, which is basically the state of our program. And what we describe in the zkApp program is kind of a state transition from an input state to output state. As part of the state, we have a counter. And as you can see here at the method, what we're going to do is we consume that input state. We're going to say, OK, we access the counter, we add 1, and we output that again. And all of that kind of describes the entire circuit. That is how it's done, nothing else. It has a method called increment. Later, when we say, for example, we get the zkApp program, which is kind of the wrapper around the circuits, we say counter.increment, and it's going to execute that. It will output a proof, and anyone else can verify the proof. Exactly. That's how we're going to use it. First, we need to do a compile step, which kind of compiles this program into the more low-level language, or does everything that needs to be prepared to actually create proofs. Then we're going to define the state. We're going to create the proof by calling the increment function, and then we get the proof. And what we can do then in the next step is we can actually take the proof, verify it using that program again, and we get an output. Is it valid or is it not valid? Part of the proof, by the way, is public inputs and outputs as well. Awesome. So how do we now actually take that programming model, and how do we interact with the base layer in a way that's kind of has a common language? And the way we do that is using smart contracts. And that's a primitive that is also offered by OpenJS, and it's used to interact with the Mina layer 1. Part of the protocol are account updates, and account updates are kind of these write instructions towards accounts. So we're going to say, okay, like update the balance by subtracting 1,000 or whatever. And let's skip that for now. So that's an example of a smart contract. It has a slightly different API. As you can see, we can define state here, for example, a counter. And then when we have a method that's that method creates a proof of account updates. And what we're going to do here is we give it the counter proof. We're going to say, okay, we started at a certain counter. We called that function that's defined in that counter proof, and we got that output. And what we're going to do here is we verify the proof, and then we take that on-chain value, we compare it with the input of the proof, and then we're going to apply that output value to the on-chain state. Again, same thing here. How are we going to use it? We first have to compile it. We're then going to instantiate it with some on-chain address, because obviously that smart contract has been deployed somewhere, or in that case, actually, we're going to deploy it afterwards. So we're creating Mina transaction. We're going to fund that account, and we're going to deploy a contract. That's basically it. Then after we've deployed it, we can now actually call that smart contract function. We're going to call counter.increment. We're going to we get the proof out of that, and we're going to create a new transaction that actually calls this contract, gives it the proof that we've generated, and we get a transaction from that. We prove it, we send it, and gets included. Awesome. So that's been kind of a small introduction to how we rewrite layer 1 programs. But for this hackathon, actually, we're going to focus on zk application chains. And these are going to be written with a framework called Protokit. And that's what I'm going to introduce now. Awesome. So Protokit in a nutshell, it's a It's built on top of OpenJS, so it's powered by OpenJS. It has the same primitives, it has the same instructions, pretty much the same API as well. But what it now kind of offers is kind of this iteration on top of the verifiable protocol and execution. And so everything in Protokit is as well proven, but we're going to use a more on-chain based protocol and framework for that. And we have a lot of built-in primitives so that we can now kind of go to that application layer without having to build everything ourselves. So we give you a lot of those toolkits out of the box. You could just reuse them. Yeah. How exactly we're going to see now. Awesome. So now kind of the question arises, basically if we have that verifiable compute and if the base layer offers shared sequencing, why do you need another sequencer? The reason for that is execution orchestration. These proofs in and of itself are very powerful to basically prove state transition. But as soon as multiple users want to access the same state, you get a lot of problems like race conditions, data races, stuff like that. So what we need to do is we need to build something that orchestrates these executions. And that's what we did with Protokit, so that you don't actually have to do it yourself. So how does it work in practice? So everything in Protokit is again proven and provable. That means that everything that happens in Protokit has validity proofs attached to them. So you can kind of think of them as a zkApp rollup. Yeah. We take those proofs later and we give it to the base layer to then be settled there. Everything in Protokit is built in a way that the sequencer operator cannot actually do something bad. They cannot be fraudulent because all of the circuitry, all of the code is provable, therefore they don't have any possibility to do something bad. We also separated Protokit into 3 distinct components, which are the sequencer, the protocol, and the runtime. And so the way that works is that the runtime contains all of the application code that you guys might build. The protocol then kind of has all the underlying circuits that orchestrate all of like the state writes, the tree that's under the hood, everything that's kind of not leaked to the user side. And then the sequencer does all of the proving, the worker orchestration, all of the kind of the DevOps that has to happen around that. So like yeah, most of the application will only touch on the runtime side. Yeah. Awesome. So how kind of that can a workflow work or look like if an application is actually written using Protokit? So everything kind of starts normal. A user creates a transaction, they only sign them, they don't do anything proven there. They send the transaction to a mempool that's operated by the sequencer. And yeah, that resides in the mempool. Then what happens when a block gets created, a bunch of transactions get collected, they get executed. And as part of that execution, they emit state transitions, which basically in our model means you have some state and that updates from a from value to a to value. And all of those state transitions also get collected and get proven based on a global shared state. Obviously, as part of that block production, the transactions are also sequenced, so they have an order, which is very important because that way we don't have race conditions or anything else that we would have otherwise. Exactly. And then when the block is proven, everything gets put together. We get one single proof that we can then use to sell on the layer 1. So let's look at some more graphically built workflow. So for example, we have Alice here. She submits a transaction to the application exchange's mempool. So then when a block gets created, the sequencer picks up those transactions and executes them. And this is the part where we kind of split it. The first is it executes the runtime. So runtime basically means your application's code. Everything will be executed and it produces state transitions. Additionally to that, the protocol gets executed that's attached to a kind of transaction. It also emits some state transitions. And yeah, those state transitions will be proven and will be then, if you go to the right here, collected into the block proof. And that state transition proof, along with that transaction proof, become the block proof. And that then gets committed to the base layer to be verified. What else can Protokit do? We can do token bridging. We can bridge everything from the layer 1 to the layer 2. Obviously, as I've already touched upon, settlement. We have a built-in archive node that collects all the data that has been historically emitted. We can also process that data using our processor. We do everything regarding proof parallelization for you, so you don't have to do that. We also offer kind of a suite of DevOps integrations, so you can host your application really easily on some server and run it in a production-like environment. Awesome. Let's look at how we can actually build applications with that. How does that look? It starts with the starter kit. That starter kit is a Git repo. You can clone it, or you can use dgit here. You clone it to your local machine. You install all the dependencies, and you're good to go. What do you get from the starter kit? Basically, what we wanted to do, we wanted to make the entry to Protokit or an end to Mina as easy as possible. So we built everything that's be used in 99% of the use cases just out of the box. And we give you kind of a toolkit of things that you can work with right away. And so as an example, that is kind of the file structure that you get when you clone the starter kit. And a big part of that is like in apps/web, you get kind of a pre-built UI. There will be a screenshot of that later on how that looks. So we built kind of a really basic UI where you can kind of see the pattern, how like the client and the server connect, stuff like that. We already built it here. And then in the packages/chain, we built kind of the rough structure of an application chain already for you. So as part of that, we already serve this balances module, where we kind of just have a super easy example of like how balances work. So here you can add balances to an account with a certain token ID. As part of that, I think also as faucet is also included, so that's going to be important for the UI as well. So we have like some basic configurations basically that you can just get started right away. You can just start that. Actually running is as easy as that. You call pnpm install all the dependencies, and then call pnpm dev. And that's going to run the sequencer in the backend and the UI in the front end. And that UI looks like that. We have some really basic functionality, some block counter in the left-hand side and the top, and a connect wallet, so you can connect your wallet. In this case, Oro wallet, which is kind of the Mina default wallet Chrome extension. And then we have a faucet here. You can connect your wallet and then get some sample tokens. And that's like kind of shows the workflow of how you get from A to Z. And then you can basically iterate on top of that, build your own application, obviously delete all of that if you want. Just basically to showcase how easy it is. Let's look at how runtime modules, basically your application code, will be structured and written. We have like basically three important concepts here. Runtime modules are class-based, so you can create your own TypeScript classes that extend a runtime module, and you can orchestrate them based on that. We offer stateful properties, so you can define a state super easily on that, and then runtime methods which actually run your code. We look at a really quick example here, voting. So here we define some structs, and doesn't really matter. Kind of running out of time, so I have to speed run this right now. So this is what a runtime module looks like. We have an annotation here, runtime module, which defines it as one. We define some state here, which are proposals, so proposal ID, and then the proposal itself, and the treasury, where we kind of keep track on how much tokens we still have in there. Then we create a function called vote, where a user can vote in a proposal. So 2 arguments here, proposal ID and the vote, which is a Boolean. The first thing we're going to do is we're going to retrieve the proposal itself from the state. We do this via this proposal.get. This is an async method, so we have to await that. And then we do some assertions here. Here in this case, we assert that it's kind of still in a valid voting period. And after that, we're going to apply that vote, either if it's a yes or no vote. to the votes that are here. We do that using a provable if. That's kind of the ONChess pendant to ifs themselves. And yeah, we're going to apply that, and then at the last step, we're going to set that updated proposal to the state using the proposal ID again, calling this proposals.set. Yeah, this is another one. I think I'm going to skip that for now. Feel free to hit me up later to get the whole example. Yeah, we can test them really easily by using this testing app chain thing that we provide. Yeah, pretty much the same as we saw before. We call app chain.transaction. We call the function, and then from there we can do some assertions like, did the state get updated? What's the execution result? Was it actually valid or not? Stuff like that. Yeah, if you want to learn more, come to our booth or go to protokit.dev. All of the documentation will be there. Yeah, we will be here the whole weekend, so feel free to hit us up anytime you see us around. Yeah, all the links are there, Discord, docs, website, everything there. Awesome. Thanks for listening, and see you around.